All right, so we're going to work through problem 4.23 from Taylor's Classical Mechanics. This is a chapter 4 problem, and it's on conservative forces, proving that the following forces are conservative using the gradient crossed with the force. If a force is conservative, the cross product of del or nabla cross F should be 0. So let's just start with our first force. Kx, 2y, 3z. So if we take this cross product, z, we're going to use this determinant to take the cross product. So we're going to have I, and that's going to be times the partial with respect to y, 0, minus partial with respect to z of 2y is also 0. So times 0, minus our j would flip the sign. With respect to x, that's 0. With respect to z, that's 0. And plus our k, that's going to be 0, and that's also going to be 0. So you can see that for our cross product, we get the 0 vector, which means that it is conservative. Now we're going to confirm this to be true. It says here in the second part of the problem, find the corresponding potential energy and verify that the force is the negative of that gradient of potential energy. So our potential energy is going to be the negative of our work for a conservative force, which is the negative integral of f dot dr, which in this case is the negative integral of x 2y 3z dot dx dy dz. So that's going to be negative the integral of x dx plus integral of 2y dy plus the integral of 3z dz, which is going to be negative. And we actually have that k out here that I forgot about from our force 2. We can just add that into here. K is a constant. We're pulling it out front. So that negative k times all of that actually. So negative k. This is going to be 1/2 x squared. Going to get our 1/2 x squared plus y squared plus 3 over 2 z squared. That is our potential energy function. Now we want to verify that the negative gradient of potential energy is our force, which is also true for a conservative force. So if we do the negative of this, negative gradient of this potential energy is going to be 1/2 times 2. I'm going to leave our negative k out here. What's a better way to write this? Let me rewrite this here. We're going to have negative k we can pull out. And have negative 1 times all of this. Then 1/2 times 2x plus 2y, or comma 2y, and this equals k. Those negatives are going to cancel. You're going to end up with positive k 2's are going away, x, and we can leave this as a parentheses, x, 2y, 3z. And this is exactly our force that we began with. And this is true for any conservative force. So we verified that the force was conservative with the cross product. We went down to find the potential function by taking the gradient of that potential function. If you don't remember how to take gradients, there is a video on that that I have, as well as solution to a gradient problem. But you're dotting this nabla operator, which is the derivative with respect to x, derivative with respect to y, derivative with respect to z, taking the dot product of that with your function. Or not the dot product, but you're going to end up with a vector with each component looking something like this. This right here is this would be the gradient of f, for example. So for the gradient of u, we just do the same thing, and each of them shares only dependence on itself. So you just end up with each component working back up to the force, which is conservative, and we just verified that 2 different ways. Now, working on part B, we have another force. The force is K times y x 0. So force equals K y x 0. So we'll start again, take that cross product. It's going to be y x 0. So it's going to be I, that's going to be 0, that's going to be 0, times 0, minus j, 0, and 0 again. That's going to be 1, partial with respect to x, minus 1. That's going to work out to be the gradient cross the cross product of the nabla operator and our force is the 0 vector. So we have a conservative force again. Now we know that our potential energy is the negative of work, so it's the negative of that F dot dr. And that's going to be the negative of K, Y, X, 0, I believe, was our force. Let me double check. Yep, y, x, and 0 dot dx, dy, dz. So we're going to have our negative k out front. Integral of y dx plus integral of x dy plus integral of 0 dz, which is going to go to 0. So now we have negative k. That's going to be xy plus xy. So negative 2k xy is our potential function. Now using the gradient of that potential, so let's take the gradient of the potential function. That's what I was saying up there. It's not a dot product. You are taking the gradient, though. So if you want to see this written out, it's going to be u over del x that's the vector that you're going to get from that. So our gradient of u with respect to x, we have negative 2ky. With respect to y, we have negative 2kx. And with respect to z, we get 0. We can factor out that negative 2k on the outside. So y, x, 0. And then we can verify that the negative of our gradient is equal to 2k y, x, 0. And I actually believe this should have worked itself out to be, yeah, the potential function that gives us this is actually just going to be negative kxy. So we can just get rid of the 2's here and everything will stay the same. And you can see that the negative of that gradient is the same as the force. And this is because these are actually line integrals and we have to go along a certain path to evaluate them. So if we go along x first, we end up with xy, and then we go along y. This is what you're going to end up with, just that xy as the potential function that evaluates to that force. And you can see that here when we prove that down below. So that's everything they're asking us to prove on that. Now we have part C. Part C is k, negative y, x, and 0. So nearly the same force that we just dealt with. So part C, our force, is k, negative y, x, 0. So once again, taking that cross product, using the determinant. You can memorize what the cross product is, but it's definitely easier to use the determinant. Pull that k out to the front, and we're going to have negative y, x, 0. Now evaluating this determinant. I, that with respect to y is 0, that with respect to z is 0. So 0i minus j. This with respect to x is 0. This with respect to z is 0 plus k. That's going to give us 1. That's going to give us negative 1, so minus negative 1. So our cross product this time does not come out to be 0. We actually end up with a 2k as our vector. So this is pointing in the z direction. It has a z component. It's not the 0 vector, so it's not conservative. This is how you would go about determining if forces are conservative. You can use any of the methods here. If you know a force is conservative and you have the potential, the negative of that gradient is going to give you the force. Cross product equaling 0 automatically proves that the force is conservative, and from there we just work through to satisfy the other requirements of this question and verify that by direct differentiation.